Hello, everybody. This is another workshop on the Reclosure November series. And today we have John Newman about Injest.
Hey folks, how you doing? So my name is John Newman, and recently I wrote a little library called Injest that helps you use transducers. And we'll be talking about it today. This is a workshop, very free form, not a one-way presentation. So hopefully we get a lot of engagement from the group. Feel free to ask questions or make comments. Who am I? I've been using Clojure for a long time, since it first came out. Started using it in the military back in, when I was in the Army. And I used it to build scripts to manage networks and systems and security, pushing out patches across a series of fobs in Afghanistan. And this was back in 2008-ish or so. So a long time ago. But as I was getting out of the military in 2010, there weren't a lot of Clojure jobs, unfortunately. So I decided to get into cybersecurity. But even there, while working at DHS down in DC, I used Clojure quite a bit to help organize and analyze security event data. And there's some parallels to what a lot of data science folks do in that space, because you have to do a lot of cleaning, data wrangling, and trying to collate data. Years went by, and the whole Clojure industry sprouted up, as we've all seen. And so eventually I decided, hey, I just want to do that full time. And so around 2015, moved into the Clojure industry. First worked for Yet Analytics in downtown Baltimore, dealing with ontologies and linked data. Really fascinating work that they're working on over there. After that, I worked for Yet Analytics, worked for Dividend Finance based out of San Francisco, and they're doing solar loans for residential installers. And so that's where I cut my teeth in the fintech industry. And now I'm over at Guaranteed Rate, working on mortgages. So still fintech, but slightly different problem space. And by the way, we are hiring right now. So if anyone is looking for a job, please reach out to me. Also, I'd like to thank Daniel for and all the SciCloj folks for their hard work on the libraries they're putting out and organizing these conferences and these talks. Really amazing work they're doing, and I really appreciate it. Also, thanks to the Clojure core team for all of the years work they've put in, and also, you know, making transducers. Pretty fun stuff. So yeah, we'll jump into it. I guess I'll share my screen out. Anybody have any comments, questions, upfront questions? A moment. So it's going to be.
I'll reiterate that.
Sure, go ahead.
I'll reiterate that Guaranteed Rate is hiring Clojure devs.
And we have lurking with us some of our Guaranteed Rate people, so we might have them chiming in. Let's keep it professional, folks. But yeah, so this is gonna be very free form. I'm just going to pretty much run it from the REPL. There's no specific presentation other than this. But what we'll go over first is just the setup. So if you guys want, you don't have to, but if you want to play along, you can feel free to set yourself up a project in whatever IDE of your preference. And in the, go ahead, show you. Getting started documentation. What you'll want to do is just bring in this in your depths Eden file And this is on GitHub under John MN3 Injest. Get to all this documentation there. You want to populate your deps even with the correct dep, but there's also this CLJ condo lint config, and you'll want to drop that in your CLJ condo path in your config. If you add this line in there, add this vector to your config paths, you will get the linting automatically. As long as your IDE has integration with CLJ condo, which means.
Hello.
Hey, how's it going? So, and then in any namespace, some scratch namespace you want to launch up, go ahead and require in this path, this require path, ingest path refer, and then these macros right here will get you started for this conversation we're going to have. Any questions about that so far? That's what I have here. I have ingest path with these required in, and ingest state allows us to add in foreign transducers to our registry of sorts of transducers that we used. So what we'll go over today is path threads. Three main things: path threads. Secondly, auto transducifying threads. And thirdly, auto parallelizing threads. And path threads are very much orthogonal to the transducifying threads. And I'll show you what I mean by that. These two macros right here, they are path thread macros, and they come out of the path namespace. And what does that do? So it allows you to drill into nested data structures in a very efficient way, both execution-wise and from an ergonomics perspective. As you can see there, the plus thread first operator is allowing you to do a get into this vector, returning the third item. Now, you couldn't normally use a number in the function position. So that's where this differs. And so that's why this would not work. Right? So we're trying to do this with that. Right? But what happens here is similar to an nth. We're doing under the covers there. And to show you how that's working, let me go ahead and macro expand that for. Let's show you some of the magic that's going on under the covers here. So there's an implementation of get or nth inside of ingest. And it basically, if you pass it a number, then it knows that you either want to do a get into a sequential thing, or you could have a map that has numeric keys. So we don't know which you mean at this location. You could mean either, that you're trying to pass to that number. And so we provide internally a get or nth that just checks to see if it's associative. If it's associative, then we're going to go ahead and try to do a get with this 2. If it's sequential, we're going to do something like an nth under the covers. So let's walk this out a little bit. Let's start with the data structure right here.
I have a question. Clojure map accepts numbers as inputs as well. So are there any issues with that?
Say that one more time. Couldn't hear that.
Clojure map accepts numbers as function arguments. Well, maps.
Clojure maps
Accept
can
numbers.
be used as functions, right?
Yeah. So if you want, you can pass a number. So it could be interpreted as an index as well. So maps kind of are indexable. I'm not sure whether they implement those specific interfaces, but they could be regarded to as such. So what do you think about this and your micro?
So your point is that you can use maps as a function, right? So you could do both of these could work. So you could go one stuff, and that could work. Or you could do, you know, zero stuff. And that would work too.
May I ask a quick question, perhaps now?
Sure.
What is the difference to Spectre? Because it seems that what you do here, I could do with Spectre as well.
You could absolutely, yeah.
So in which situations would I want to use your macro-based approach, and in which situations would I want to use Spectre?
Sure, yeah. Let me answer that. Let me answer this first question first. So this could work, this formalism where you're passing it in, but in the event that something else flows through, then you could be passing a number into something that's not expecting it. And there's different pros and cons there, but if we were to simply provide
well, I understand it is a sensible default to handle both cases.
Yeah, well,
so that it wouldn't crash. Yeah, because in data, I worked in there, and generally, if there are 5 failures in the data import, you don't care.
Yeah, well, to your point, there's cases where you could just not use this get or end under the hood. We could simply always pass the parameter as to the thing, and the thing, we're expecting it to know how to deal with numbers. Maps know how to deal with numbers as lookups and vectors. They all take their first param as a lookup, right? So that could work, but in my testing, there were these edge cases where this can break your expectations unexpectedly. And so I went with this, but that's still under exploration.
All right.
Yeah. The second question, Spectre. So Spectre is a highly optimized data structure navigation and manipulation tool. And with it comes a number of, it's kind of like a DSL. And some might call this a DSL as well, but I'd say they're a little bit different in that regard. This one leans on Injest and its path navigation abilities, leans on the semantics of get in and other more traditional Clojure idioms that you're already used to. Whereas Nathan Mars's library, it gives you much more tools to drill into data in unique ways, and it's much more optimized. So if you have a problem where you're dealing with extremely nested maps and you actually want to manipulate them, you want to update them in place, then then I would recommend using that library more so than this one. This is more for the path navigation abilities of Injest are more for getting into the data, not necessarily updating it. And when you're dealing with threads, these thread last and thread first macros, you're oftentimes starting off, especially if you're dealing with a map of nested maps and the keys are always keywords, then oftentimes you'll find yourself doing A, B, C, and now I'm under C. We have a vector, and in that vector we return, we're going to map something over what we finally drilled into. And that's really in those cases where you get some big payload from GitHub, for instance, with a bunch of commits and deeply nested JSON, and you have you want to map some operations over some array within that JSON. Well, you don't have to use separate tools to drill into that data. If you keywordize all of those JSON keys in that highly nested thing, then you can just use these keywords and you can drill into the data structure before doing what you want to that sub nested part. And so this is a common idiom that we do in Clojure using keywords. And what these path threads avail to us is simply the ability to also use numbers or strings to get into these highly nested data structures. So what it does is it takes an idiom that we're already used to, and it's a very simple one, which includes using threads to drill into maps using keywords, and it combines that with the more generality of get in, and allows you to drill into things using just those intuitions that you already have. You don't have to learn any new anything new past this point. But if you're dealing with such situations that are very difficult to update, highly nested structures, I would recommend using Nathan Mars's library to that aspect.
If I understand, this situation can occur if you have half-parsed data. Some of it may, some of it may be parsed, and some of it shouldn't be or doesn't.
Right. So sometimes when dealing with JSON data, for instance, we can't keywordize the keys, right? Sometimes we're having to deal with some kind of integration with some service that returns JSON, and for whatever reason, we don't want to do the keywordization because maybe we have to spit this data right back to another service, and it requires JSON. So the conversion isn't worth it to us in that case. In that case, instead of keywordizing everything, now we have keys, we could just use the strings. You can drill in to them using, right? So whereas normally you would do, this with a nested map with keywords, with this, you could just do this. In the event that you're not able to fully, parse that thing that you got. And also you can use the numbers there. So it kind of just makes the idea of drilling into things using threads a little bit more robust. But let's go ahead and let's just walk out this example real quick. So we have this data structure right here, M. It's a map of one key value pair with 1 as the key and this as the value. There's a vector inside here, we're calling rest on it. And so the point is the value of 1 will be a sequence returned. Not just a vec, but a sequence. And rest will make ignore be ignored. Now we have 0 through 1, and then a map as the third item. Then we have the first key in this map is B, string B, and it has a vector value with a 0 and a 1, and then another map with C, a keyword C, and Bob as the value. Now, let's go ahead. If we pass 1 to that, thread it through 1, then it's going to get the 1. And let's see under the covers how the magic works. You see the get or nth M1, makes sense. And now we're getting, what are we doing here? We got 1, rest ignored the ignore thing, and then we have 0 and 1. We called 2, which is this guy, this map. So it's the third item, and that's what we're getting there. That makes sense, right? And then we can see that down here, it's just doing what we expect with thread last. Right? Now we have this map. Remember, we have the map up here with the B. So all we do is pass it the string. Now we're getting into the more nested part. And we can see how this works. We know that the user thinks if you're passing a string, this is not a vector, obviously, because you can't do lookups on vectors. We expect that the user expects that they're trying to look up a string into an associative data structure instead. So we simply pass the B to the result of everything else, which and maps are able to use that. Next, we want to get the third item out of what's returned, and that is C Bob. Expand that, and we can see what's happening there. Now let's go ahead and grab the value of C. We have Bob. Let's go ahead and expand that too. And here, C becomes a function. It's put into the function position because this is how actually threads work already. If you put the keyword in your thread, the top level of your thread, it's going to put it in the function position. We're not changing that here. We're letting that stay. Turns out in Clojure on the JVM, it's a little faster to pass the keyword to the map, but to keep things as simple as possible, we're going with the existing semantics. And then we're going to call name on the Bob keyword that's returned, and we get a string out of it. You can see name is put in the function position there. We'll go ahead. Now, here's another feature of path threads where you do not need to wrap functions in containing parentheses. And normally you would, and that'll still work, but you don't have to wrap them in parentheses. You can simply do that. One of the benefits there, other than being more concise and clear, is that this traditional way of always wrapping functions, when you see this, are we passing other arguments to this? Like 1? If that happens, now we're passing 2 arguments to this. And then once you get right here, you're scanning the code, you're looking at it. You get to right here, you say, oh, no, I've hit a function. Now I know I'm passing some stuff from the left to the right into that function, but am I passing other arguments in there? And here we are, but sometimes we'd rather not. And really, when we're threading things, more often than not, we do not want to pass something extra. And by doing that, we're signaling to the reader of the code that this code only takes one argument. So there's that extra benefit there too of conveying more information. And we can see how that works. Here you see the function that creates the string, put in the function position. And then we can also print. And the same thing happens. The print line goes into the function position. And here's an example of, we're just using it like regular thread last, no thread path thread semantics taking place in this thread. Now, we've discussed, that's pretty much the long and short of the path thread semantics that Injest provides. And this bit of functionality is completely orthogonal to everything that's going to follow. So you don't need to use this at all. You're not forced into this. And if you'd like, if you don't want to use these path thread semantics, you don't even need to. You can require the transducifying and parallelizing macros from the classical namespace. And then these guys right here won't have the extra semantics, the path thread semantics that these do, which is fine. But really this benefits situations where, like was said earlier, you may have just partially parsed results. And you want to drill into stuff before you just start doing your mapping operations or your filtering or your expanding operations. Okay. So let me see here about my example stuff. We're going to start getting into the transducifying stuff next. So let me just pause and take any questions about this stuff I've discussed so far. Fairly simple.
Sorry, go ahead.
No, go ahead.
Yeah, I had a quick question. If you go back up a little bit, actually, I think you're there already. No, you're already there. When you said earlier that the string function doesn't get wrapped, I don't know how to express it. You said you don't need to wrap the arguments to str when you use a regular. When you use your macro, the plus path, could you just elaborate on that a little bit? I was trying it at my REPL, macro expanded, and when you don't wrap the function in parentheses, it still writes a function that will accept the previous argument. I'm sorry if I'm not clear, but anyway.
Yeah, I don't quite know what you're getting at, but I could maybe riff off of what you're saying a little bit there.
Just basically, yeah, if you can just explain the difference between the X, how do you call the path macro? Plus, greater sign, or is that like a colloquial name?
Yeah, you can call it a path thread, and these plus threads are path threads. I call them path threads.
Okay, path threads, great. Yeah, if you can just briefly show the difference between the path threads handling of the stir form you had there, example, versus the vanilla thread last macro.
So with stir, you can do this, hi Bob, it worked. And so you don't need to make it a function. But suppose you want to put an exclamation point at the end. So you want the thing to go right here. Well, you could get fancy with a more fancy thread macro, right? That allows you to put things in different positions instead of the first to the last. We have those.
Yeah, sure.
But instead of doing all that, we could just make it a function.
Yep.
And this is how you would normally do this,
Right,
right? You'd wrap it in parens.
exactly. Okay. So basically, what you're saying is that you don't need to do the extra wrapping with the path macro.
That's correct. You don't need to, but if you wanted to pass an extra thing, two different things, then you would have to wrap it.
Okay.
Right? That's the only way to do it.
Yep. Okay. Thank you.
Yep, no problem. But if you're only passing one thing, then why use the surrounding parentheses? This is just superfluous surrounding parentheses. Doesn't help us. In fact, it makes it harder to read the intent of the writer that we do not want more than one parameter here. That was their intention. And by not wrapping things, they already know that by the time they get here.
Yeah, I like the idea because I've always been reluctant to use the AS threading macro, where you have to manage constantly a new name, and so
indeed, as thread. Yeah.
Sorry, go ahead. Go ahead.
Yeah, like you're saying, the as thread macro is what you'd oftentimes use to handle this situation, but then you have to do this, use the same semantic across the rest of your thread. So
yeah, as a matter of fact, I find it preferable even than using the as thread to simply use a anonymous function like this and wrap it every time I need to change the order of arguments. So if your macro palliates the need to do that, that's really nice.
yeah, right. And it looks good too. It's smooth. It's
Okay.
You know, I like the way it looks.
Thank you.
It's aesthetically pleasing. Yeah, sure. Any other questions about that there? Here this is working just like your existing thread last macro. Works the same. You know, this is what thread last does to your stuff. It reorders it. But let's get into transducifying. All right, so this is the X thread last. And what happens here is, let's see. Let's organize the output of this macro expand and see what it's doing. So it takes a range, and there's an XFN function provided in the implementation namespace of Injest that will take a vector of vectors, where the internal vectors are a transducer in the first position, and the remaining positions are the initial parameters to your transducer. And to show you how that continues to work, here we just pass two mapping inks to a range.
But it doesn't yet produce the transducer. It will do something with it, right? It will create it later.
Right. Well, just like with transducers using comp, you can comp together a number of transducers for use later, right? And so that's the same principle we're using here, because we can delay the composition of these things until a later time, or the execution of their composition to any time. We're using that same idea here. And I'd like to show you the implementation of XFN as well. And for that, I'm just going to take you straight to the code. And it's in here. And here is XFN. So we're taking this TS. That's these. TS is this value, these vectors. And we compose them together using compose transducer group. And all that does is applies comp to them, just like you would do with a composition of transducers, right? And so what you're ending up with is something like sequence comp map inc range. So that's what's happening under the hood, and that's what XFN does for you. Creates this guy, but makes it a function that we just drop in to our thread at that location where those contiguous, and these are contiguous. So it's finding which transducers are contiguously placed and putting them together in a common composition, just like we would want to do with transducers. Just doing it for you automatically. Does that make sense?
Yeah, I have a question. Do you then pick the output data type?
Say again?
Do you pick the output data type?
So the output data type is sequential, and we assume that the input is sequential. And really that's when dealing with a thread last formalism, you're really buying into this sequential idea.
Okay.
You're assuming that we want to do something over a sequence. And so it is a sequence. Under the hood, we turn things into vectors in certain places, especially where it's more efficient to work with as a vector, especially with old, as we'll see later, parallelization. But yeah, the return type is a sequence.
What if I would simply made it so that it would return into, for example, a map? Would this work?
Depends. What? Not sure what you mean, but I think by showing you a little something here, I might help you understand. So, oops, I've done that today.
Oh, yeah, that's fine if it's supposed to be worked with sequences.
Oh, for this, let me 10, right? Where are we? So, I mean, you're saying, what if we're returning a map?
What if I would like to create a map from these, or a set from this list, instead of creating the list?
I mean, it's just like your existing thread macro. So you can do it as you'd expect. However you would accomplish that with the existing thread macros is how you would do that here. You can turn this into a set here, and that would, for instance, deduplicate things, but the take will then turn it back into a sequence because that's what take does. We can't do a set on that. It's too infinite.
Okay, thanks.
Make sense?
Yeah.
Okay.
I have a quick question just as a follow-up.
Sure.
The X thread macro expands into a sequence. I guess if you wanted to use ingest on something like a channel or something like that, is there some kind of adapter that you provide as well for
No,
Okay,
No, no,
Okay.
and other things like that. So, you know, you have these other transducing contexts.
yeah, it's
Transducing
always possible
contexts.
to handle.
Yep, and another word for is transducing processes. And, you know, channels they are transducing contexts. They have built in the ability to handle transducers.
Sure.
And there may be other transducing contexts invented in the future. And this may not work seamlessly with them. And various transducing contexts may not work seamlessly together unless they're built to do so. So it's really more like transducers themselves are these generic things that can be used in different contexts.
Yeah.
And there's a sense in which you could consider this its own transducing context.
Okay, thank you. So basically, would you say that Injest is basically targeted at facilitating the use of transducers for the Clojure core data structures? Would that be fair to say that?
Yeah, for right now, it's more focused towards your your core code where you would use a thread last.
Okay, thank you.
Yeah, and where we use thread lasts are for, you know, our getting stuff, meat and potatoes, getting stuff done in our core code. Whereas in the future, we may make this thing more aware of channels and things like that. I think, you know, range, I think, has a iterator view over it. And perhaps if we noticed that and said, hey, no, give us your iterator version, we may be able to optimize downstream transformations. Various ideas like that where this could be optimized, but right now it's more generic and general. But, you know, if you do a channel and put a take somewhere there, you know, just like your existing thread macros, you can do that there. So, but there may end up being some boxing in between the things unless we make Injest smarter, more aware of its surrounding contexts so that it knows not to box things between steps, right?
Thank you.
Any other questions there? Here we're going to get into a big one. Here you'll see, let's go ahead and show you what this compiles down to. Catting. And here, everything. These are all transducers. So they all got, because they're contiguous, they all got brought together into one XFN. Right? So that's good because it'll go a lot faster. Here's an even bigger one. I'll show that. What I'll do is I'll show, though, this one, which has a map V right in the center. Okay. Well, I'll go ahead and no, I'll just show this one. This one's got a map V in the center. What we'll see is how that breaks down. All right, so what happened here? We have an XFN for the first part until we get to the map V. And then that breaks our chain, our transducer chain. But we start another one right here for the rest of the transducers. These get put into a transducer group for going fast. These get put into a transducer group for going fast. And the map V has been composed into the center of those. And then we pass the range right here. Now, we could do all this by hand. And once you start to learn transducers, you're able to think like this, and you're able to just imagine what the correct, sequence construction might be, or transduce construction might be. And you'll be able to convert between thread last and traditional transducer versions. But this allows you to hit the ground running with what you already know about thread last. And it'll just automatically do what you wanted it to do for the most part. Okay.
A question. So this map V is simply added into the XFN function so that it would fork whether it is found, right?
It's not added. So it's not added into the XFN. This map V is not added into the XFN. In fact, it's kept separately. See, everything that came before it, these things, all got put into this XFN.
The question was a bit different. Whether you simply added the list of functions which you have to look for, whether you want to fork in there or not, right? It's
right.
In source.
Yeah. So okay. in the source, there are each of these are essentially recorded as being transducers. Map V is not recorded as being a transducer, and that recording, that registry, is in state or data. These are the parallel registrations of things that are transducers that can safely be used in parallel. And here are the registrations of just your transducers, whether they're safe in parallel or not. And here they are. And there's no map V in there. Map V has not been defined as a transducer. So that's why when we get to the map V, we say, oh, this is not a transducer. Stop collecting transducers and just bag up these ones.
Okay, thanks.
Yep.
Can I ask you a quick question regarding the performance?
Sure.
I apologize if I ask you to repeat yourself, but you're saying that XFN will improve the performance of a hand-rolled transducer? Is that correct? Or
no.
Okay, sorry. Okay.
It improves upon the performance of your traditionally lazy thread last operator.
Okay, thank you.
But it gets you close to what you might write by hand. There are situations where you could foresee things better than what our macro does here, and perhaps squeeze you some more performance juice out of transducers. And so, but ultimately, this is going to get you 95% of the way there. You're not going to get more than like 5% or 10% by doing this by hand. And that's okay to do that too, to build it all by hand and squeeze every last, ounce of juice you can get out of it. It all depends on, how hot that loop is and how important it is for you. But okay. This makes transducers such low-hanging fruit and so easy that it's like, why not try it? And if it does work, well, then if this is a really hot loop, then maybe you'll want to rewrite it using the canonical transducer syntax.
And in that case, you would probably be testing every scenario.
Yeah. It's also easier to get things wrong when trying to compose transducers together, especially if you're new at it. It's easy to get things wrong. But that's just a familiarity thing too. Over time, as people become more used to transducers, it may become a lot more obvious to folks. This makes it easy. So going a little bit further, here's the registration of foreign transducers that aren't part of Clojure core. And so they're not in here, right? But we can add to this registry using the state namespace. State namespace takes in that default data, and it registers everything. And if you call this, essentially updates the transducibles atom with your symbol that you provide. And here we're providing X forms from Christoph Grand, his reduce function there, and we're adding it to our registration, our registry of transducers. Now we can use it down here. That was a big number, so it took 2 seconds.
So basically, doing a registration does give you the ability to do more optimization when you invoke your macros. Is that correct? When you register a transducer, let's say a third-party library transducer, like Christoph Grand's macro, you're telling the Injest framework, this function, when you encounter it, you can treat it this way or that way.
Yeah, you can treat it as a transducer because transducers aren't tagged as being transducers in their metadata as such, anything like that. So we don't know what a transducer is.
Right. Okay, thank you.
Coming in as a transducer, right? So you have to register them.
Right.
I'll go ahead and show you what it looks like.
Have you thought about using metadata to tag functions as being transducible? Or
could, but the core functions are not tagged as.
Yeah. But like for additional like user-defined functions.
That would be possible if we say, hey, everybody, let's have a convention where you go ahead and tag your stuff as being a transducer. Then you wouldn't need to do registrations because your stuff's already tagged. And we wouldn't have to check for the registry for that. We could just check as it flows through, which would be great, but it's a convention that everyone would have to sign on to.
Or you can also make a function atom where you specify your own function, which would look your metadata and then decide for you for that specific project.
Say that one more time, Martinez.
Imagine that you have an atom of the function that would extract the metadata and decide whether it is reducible, whether it is a transducer or not.
And how would it figure it out?
I would set the function in my own project. And then I would tag my own transducers as I want. Let's say letter of the first method, let's say first letter of my method is going to be T, which means it's transducer.
Yeah, or X or something like that. Yeah,
that's something very stupid.
Yeah, that's another way to do it as a convention, which may work. Time being though, and here we can see that what got created here is C Grand X forms reduce got put in. And if it wasn't in there, it would have been placed outside of the XFM.
So for example, in that function, if you have this kind of function which you can specify, you can simply check the namespace.
Sure, there's like multiple ways you could do this. Multiple ways you could communicate to your own users or your own consumers of your code base how a thing may or may not be a transducer. lots of ways to skin that cat. Ultimately, though, a registry solves all those problems. It has its downsides, having a registry, but it's good enough for right now, for sure.
Yep.
Yeah, and you know, the surface area of macros or of transducers in Clojure core probably won't evolve extremely fast, you know. And you get added, we'll throw them in the default. But yeah, we're coming up on an hour here. Up next, we're going to start talking about parallelization. But how are we doing, Dan?
So wonderful. Yeah, let us think if it is a good time for a break, or maybe you would like to continue a little bit. And what do you think?
Yeah, I think it's a good time to take a little break. I'll grab some apple juice myself. Maybe bust out my cowboy hat. I don't know. We'll see. But yeah, let's take a fiber.
Great. So 5 minutes, everybody. See you soon.
Hey, folks, we're back. And Florian has a question for us. Florian, can you repeat the question?
So my question is on the why you need the transducer registry. You explained it, but I didn't quite get it.
Yeah, sure. So it just so happens that transducers are just functions, and they're not tagged as being transducers or not transducers. So if you see a function coming in as a parameter, and you want to do one thing with it if it's a transducer and do another thing with it if it's not, you don't know ahead of time whether it's a transducer.
But the transducer, I think, has an API that you have to have three ways to call it. One with zero arguments, one with 1 argument, and one with 2 arguments, I think. So from that, couldn't you determine if something is a transducer or not?
If you were to use some meta programming where you reflect into those functions and then try to gather what their arities are and whatnot, you might be able to heuristically determine that it might be a transducer. But I don't view that as it might be possible, and there might be a solid way to complete doing that quest, but I think it's a hard thing to do.
Okay, got it. And the second question is why do you need to determine if something is a transducer or not?
Because what we're doing here is we're taking a thread last form with a bunch of forms in it, and we're scanning them. And for those that are transducers, we want to find all the contiguous groups of transducers and then compose them together into one transducer. And so for that purpose, we need to scan and find them.
Okay. So this would work with, so a transducer can like be something that is like similar to a map that returns like a sequence with the same number of elements as you put in, but it could be also something that returns more values or less values. So what you say, you are able to inspect the entire thing that way. So in a way, this would be something that is more advanced than using Spectre, if I may have this comparison, because with Spectre, you just can operate on the data structure that is there, but you're operating on a data structure that gets sort of compiled at whenever you call it. So that should be more powerful in a way.
Well, now that we're at the transducing part of this presentation and the part of ingest, it's not just path thread semantics, but it's transducing stuff. we're now going down a different path in Spectre altogether. Yes, this is a different thing, and it provides benefits that are not there in Spectre necessarily, unless Spectre is doing some transducing under the hood. But Spectre has lots of optimizations too, so could be doing some stuff like that. But the purpose goes a different direction here.
Okay.
Our purpose here is to transduce, and yeah, I mean it's arguable, but again, like it's a different, I'd say it's just a different cost benefit kind of thing, and it's for different problems. Spectre versus this.
So I'm sorry if I ask something that you perhaps will put for in the future. This to me like rings a bell that this should be something that is extremely powerful, and I am trying to think of situations where this could be useful, and right now I'm not I don't have any idea where it could be useful, but possibly like you could sort of do a like if you have like let's say you have like certain events like log events that come as maps. So in this case, you could use your library to sort of filter them dynamically and print out only those events that we are interested in.
Indeed, yep. You could filter, and filter is a transducer, and anything that you would be able to do with ingest, you can also do with the regular thread last macro. Okay, so it wants to be isomorphic in that way. So if traditionally, when trying to filter a log of warning maps or information maps, and we want to filter them, you could do that with a thread last and just using filter. Or maybe you want to map over them first and then filter them, or do different things. Where you find yourself wanting to do that, you can also use ingest. And all that's going to change is it's just going to be more fast and maybe use less memory. But everything else, the execution semantics change a little bit, but syntactically and semantically at the code level, you're looking at the same thing. And that's just one of the happy accidents that the way transducers ended up being designed made it so that they're easily composable together in such a way that's almost the same as thread last. And that's in the docs, for transducers themselves. And so you can think of it like a thread last. And that's really the key insight here. And so where you'd want to use it, it really comes down to whether you're in a situation where you would have a thread last, but you just need more performance out of it. It's pretty general. So let me get back into the flow of things here. So we're going to start talking about parallelization. So we want to parallelize automatically those things within our thread that can be parallelized. And this is an area that has caused some foot shooting in the past too. Folks when transducers first came out, people got into them, they were checking them out, and people made examples of the parallel version as well. But some of those old examples are also broken because they didn't realize that some of the transducers cannot be used safely in a parallel context. And so you need to keep that in your head. Okay, which of these transducers are parallel? Which of them are not? And we don't, again, for that last discussion, we would need a tag for that as well. Besides just tagging it as a transducer, we need to know if it's tagged as parallel transducer. So instead, we just have two registries. And I also want to make a point real quick about the kind of parallelization we're dealing with here. Because we're dealing with sequences, this is a certain class of parallelization that doesn't apply to all kinds of parallelization. We're coming from an input sequence which is ordered and sequential, and we want to go back to an output sequence that is ordered and sequential, and the input and the output are correlated. And so there's certain performance limitations when you're dealing with those kinds of parallel problems. You're going to run up against a certain intrinsic amount of thread communication and thread coordination and overhead when trying to go from sequential back to sequential. And so as things scale, as you add more and more cores, you're not going to just, for every core you add that much more performance to the parallel process. If your problem was truly embarrassingly parallel, where your inputs were uncorrelated and your outputs were uncorrelated, you could literally run the same job on two different machines that don't talk to each other. And as long as it's the same program servicing two different users, then you could call that a distributed system. You can call it a parallel system, but really, and you're maximizing the efficiency or usage of each of those machines. But because you don't have to communicate back, you can ping 100% on each of those boxes. Whereas when you have to bring the stuff back together, that's when you're going to run up against some limitations. And what I've found is that the more cores you add, you get down to around, once you get up to 32 cores and 64 cores, you're only going to get about 40% of all of your multi-core juice. And the other 60% is lost on coordination and thread communication. I think that can be improved if the JVM itself under the hood gets a little bit smarter about this stuff, and maybe there's things we can do on our side too. But ultimately, there's always going to be some amount of overhead that, and in fact, when you're dealing with only two cores, you have the least amount of overhead. So when using two cores, you almost double your speed. When using four cores, you're getting closer to 75%. You use 8 cores, you're getting closer to 50%. And as you go up, it starts to slope and plateau in terms of how much you lose, at least as far as I've seen in my testing. But I wanted to give you a little bit of color there. So we'll go over a few examples of the parallel version. And then I'll go over a few pretty pictures of some stuff I made in the past that show the performance metrics and where the cost benefits fall out and where you'd want to choose one formalism over the other. Okay, so let's do it. Let's jump into the parallel stuff. So I made this little macro, time val, and it just gives you the values. Might not use it too much here.
Sorry,
I
John.
have a
Sorry. I have to share my screen. Huh?
Yeah, I have a question. Do you think it would be useful for to have a factor function that would create this, let's say, thread through macro, so that it would allow, well, not then it wouldn't be a macro anymore, but for example, what do you think, whether it would be useful to have a factory so that you would be able to supply some kind of parallelization or maybe sequence conj strategy and so
on? Factory function to do so. What do you mean? For what purpose? Can you expand out the idea or the purpose that you're getting at? Certainly would be cool to have a thing that more easily lets you create transducers, but if that's what you mean, like there's, it would be nice to have a thing that helps you create transducers more easily, I think. But that's like creating these things, you know, it's not.
I've just posted a code that I use to create transducers. It's the def macro indicator.
Chat here. I don't think I can see the chat.
So I use that a lot to basically have to create functions that where the transducer itself would return always one value for one input. So anything that can be mapped on, I'm using this this macro, and it makes it so much easier to write transducers that way. But
okay, did you drop that in the Zulp?
In Zulp? No.
Drop that in the Zulp. Is that where you put it?
No, I put it here in the chat in Zoom.
Okay, I'd recommend putting it in the Zulp just for posterity, so I can get back to it and check it out. I'd love to see that. It's something that helps make transducers?
Yes, yes.
That'd be cool. All right.
John, another small comment. There was a suggestion to, if you could maximize your VS Code, and then it is kind of more visible if comfortable for you.
Like that? And
yeah, thank you.
Yeah, and I can try to go a little bit bigger for those. Yeah. We're going to get into that part.
Would you mind me asking a stupid question as well?
Sure, please.
It has nothing to do with ingest, but if you are if you're working with stateful transducers, I have noticed that at least I'm using atoms to keep the state of the transducer, and I posted a very simple one. Stateful transducer I use in one of my open source libraries, and in many ways, when you deal with reagent reframe, and if you deal with normal atoms, you get shielded away of this sort of complexity, and I'm thinking like might be a bad way to do, or it looks strange to me.
I suggest to maybe remain on topic with ingest today. Yeah, sorry, that's fascinating, Florian.
I'm sorry.
Yeah,
sorry.
That is fascinating, and yeah, for atoms, for stateful transducers on the JVM side, if you use an atom, you might be protected from some of the hazards of multi-threaded aspects there. But a lot of the core stuff uses volatiles, and which is a little less safety, but helps you get more performance. So, but let's just jump into real quick an example here. Work 1000 is just doing some work thing 1,000 times. And here is a bunch of sequence transformations that we've seen previously in the README for the project. It's very similar to that, and it just turns it into a string for passing on to the result. We don't actually care what the work is. We're just throwing it away. We just want to see the stuff go fast. So, and here is, we're using transducer thread last. And then on the outside, we're using fold thread last. And we're mapping this work that we defined here. So we give it some input, we do the work, and we just keep on passing along. We're not actually passing anything because I didn't care about making it solve a real world problem. I just wanted it to compute for you so you could see. And what is going to happen here? So, man.
So what is the result of X mark work? Is it a number or is it a sequence of that first?
It's actually just a string. It's actually just a
Okay,
string.
so a single value.
Well, no, we're reading the string. Yeah, so it's a single value, and basically we're taking as input some number. Result, but here's where the work happens. So we're taking work function, and we get the range. So what the work function does, work 1000, is it's returning a range, but we're giving it a single number. Again, this is all just to make work happen. Try not to think about what problem we're solving because it doesn't solve any problem. But as you can see here, we're up to 8 seconds. And I'm not going to take the time to, how long is this go? 50? It's a little bit long. I'm not going to take the time to plot this out for the workshop so you can see the plot. But what I am going to do after this is show you some of the pictures of the outputs that have been already made. But that needs to get interrupted. And what I'd like to do now is show you what happens with one of these. What I showed you before was the macro expansion of this with a map V in it. This is the transducer thread last. And I showed you that this broke apart our XFN into 2 different XFNs. Our map V did, if you recall. Same one though, I'm going to now show it to you with the fold version. Let's see what that starts to look like. Just so you know how it works under the covers when we're dealing with.
So a question, does fault result in a sequence or is it going to return in a value? Or is it still the same? Is it still on for the sequences?
What do you mean the return?
Well, if the return value of the transducer output of everything, of all of this.
Well, normally it'll return a sequence unless your thread that you're defining, like if you call first as the last function in your path, in your thread, then you will end up with the first thing in that sequence. More often than not, you're going to be getting sequences and returning them because we're talking about a thread last here, and what thread lasts do is the operator of the sequence. So if you just have a map, then the result will be a sequence. But if you have map first, well, then you're going to get the first thing out of that sequence that the maps return.
Why I was asking it before? Well, I was asking it because I don't understand why do you want to have XFN and then fold XFN variants, 2 variants? Why do you need that? Why do you need 2?
Fold is the parallelized version. And
okay.
so here's what's happening here. So And what this does under the hood, this guy, it's going to scan these and look for transducers. First, it's going to look for parallel transducers. Map is a parallel transducer, right? Let me see. Filter is also a parallel transducer. You can see that here. Here's the top of the whole chain. Map Inc. Map Inc. And then the filter and the mapcat, those are all parallelizable. But once we get the partition by, that's not parallelizable, that's stateful. And so we have an XFN. And so point being, if you don't have a parallel transducer, but you do have a transducer, then fold will just drop down to the X greater than version semantic and will give you an XFN. So it provides two optimizations. It will parallelize what can be parallelized, and what cannot be parallelized, it will transducify. And then we see that right here. Partition by is turning into a transducer. Next, we get to a map, which is foldable. It's parallelizable, and that gets done there. So that's what happens under the hood there.
May I ask a question, John, about the concept of a parallel transducer? I was looking at the data, the registries in the source code, and there's about half of the total number of transducers that are considered parallel. And I was wondering if I've never used fold. Well, I've used it just to play with, and I've forgotten how to. But could you give us a formal definition, if there is one, of what a parallelizable transducer is versus one that isn't? For example, I see that cat is parallelizable, and of course, map and filter. I can see, I have trouble seeing the formal difference between. I can see why, for example, map is parallelizable, because you apply a function to every single element. You could just apply all of them in parallel and then reconstitute afterwards. But for example, filter, I don't see how that can be. Well, I can see filter being parallel too. But maybe cat or map cat, I don't see how this can be parallelized. Can you give us like a formal definition of what is a parallelizable transducer? Thank you.
Well, I can't. Sorry, I can just tell you that if it needs to have state, then it's kind of dangerous. But even if it does have state, I think some folks, it's possible to create a safe parallel transducer, even if it has state, if you're very careful. So a hard and fast rule of when it can and can't be done, I don't think I can give that in a short time frame. But and I would agree, some of these are somewhat mind-bending as to how they're implemented. And so, and like,
maybe there's a simpler way. Maybe there's a simpler way to ask my question. I'm sorry. Could you give us an example of a usage of a parallel transducer, a single transducer? Let's say, take while, which you just highlighted. And then maybe combine that with another parallel transducer, let's say filter. How would this be done in a parallel world with fold? Thank you.
Yeah. So one thing I should state as well is there's also Core Async provides pipeline, and that's another parallel transducing context that you can pass transducers to. And this library also provides a version of a parallelizing macro that uses transducers uses pipeline under the hood. In testing, the fold version versus the pipeline version, almost every scenario, fold outperforms pipeline. It's also much more forgiving when dealing with embarrassingly non-parallel problems. And so I've pretty much demoted the pipeline version and suggesting folks prefer the fold version at all times. Under the hood, fold uses JVM's fork join pool protocol and infrastructure. That stuff's pretty smart. I think it's very smart about being forgiving on light sequences, and I think it keeps some stuff on one thread rather than spreading it across threads if the workload is lightweight enough. So I think it's very smart about that. So I would suggest it for playing around. When it comes to, you know, why would I use the parallel version? When do I do that? Why would I want to? I think it just comes down to you want to squeeze more performance out of this thing. There's lots of other uses for parallelism, which is to include side effects. And you just want to do things, you want to make side effects happen in a non-sequential way, or that you just don't care about sequencing. And so,
Yes.
really comes down to the fact that you want things to go faster. Hey, folks, yep, they muted. So it really comes down to wanting to make things go faster, and you already have a thread, you already have a pipeline of transformations. You already know the results you want. So now you want to see if you can get to that result faster. And certain of these things in that pipeline can be parallelized. And so it's not as if we're trying to solve an intrinsically parallel problem. You're going from a sequence to a sequence. What you're wanting to do is just make it go faster. And this will automatically find the ones that can be done in parallel and then bust them apart, put them back together, back into a sequence. Does it automatically for you all under the hood? In constructing, my point in showing you this was to show that constructing all this by hand is going to be even more error prone. You're automatically getting non-parallel things to turn into transducers, and those things that are parallelizable are becoming a parallel transducing context. And getting all this to do this by hand, eventually, if you do it enough, it'll be second nature to you, but this allows you to do what you already know and organize these things in a sequence of transformations that you already know. You know, so ultimately, the fact that we're parallelizing things isn't letting us do things that we couldn't have done otherwise using just regular thread last semantics. It's solving the same problems, and you should use this to solve the same problems that you would normally solve with a thread last series of transformations. Does that make sense?
Yeah, thank you. So you can say confidently that somebody who doesn't know too much about what can be parallelized or not can just use your work macro, or I forgot the name, but the parallel version of your macro to mix them together, and at the end should come out something that makes sense if it can be made sense of. Correct?
Absolutely. Yeah, this makes it easier for you to use the power tools that Clojure comes with in a way using the idioms that we're familiar with as people who are either, you know, beginners or intermediate level users of Clojure.
Yeah, okay, thank you. I'm still have trouble wrapping my head around why, let's say, take while is parallelizable, but drop while is not.
Yeah, I mean, take while clearly has some state, you know, right?
But take while also does, but it is parallelizable.
Right.
Drop while is not parallelizable. So I was wondering if you can illustrate differently.
Well, you know, take while, you're kind of dealing with the front of the thing, so you can kind of just collect into one thing without.
And then forget about the rest, but drop while has to keep what's ahead. Okay.
You don't need an extra piece of state besides what you're reducing into. Whereas drop while, you need to remember something until you get to the rest of it. But then again, I don't think there's hard and fast rules here. I bet you people could invent parallel safe versions of a lot of these things. Maybe they won't be as fast or performant, but some of these may be able to turn back into parallel versions.
I think it might be a great idea if you have time, unless somebody's already done it, and maybe it's been done in the general Clojure community, but to write a nice blog article about precisely that.
It's a good question.
Ray does that. It's a
Well,
good
I think I thought of an implementation. First, you index everything, and then you parallelize them, and the filtering happens in parallel if it's pricey, and then you can gather again.
Yep. There's a, you know, even though transducers were invented a few years ago, we're still just scratching the surface of what we can do here. So, but again, Injest is about making all those cool things just a little bit easier. And the actual meat and potatoes of how to go like build the transducer, for instance, that's more so for the prior talk that Ben Celeste gave about how transducers work under the hood. And it's really instructive to re-review his transducing workshop prior to reviewing this one. But let me go ahead and show you some pretty pictures.
By the way, John, we have about 15 minutes before the official end, in case it helps to know.
Okay, thank you for that. Appreciate that. What I'm going to do here, this is a forum post on Clojureverse where I went over lots of what I was seeing about the performance of these different scenarios. Here you can see blue, red, yellow, green. And the green one is your traditional thread last macro. That's dash greater than, okay? And what we're doing here is we're testing, we're doing 100 times this value, and we're increasing n each iteration, and we're taking 1,000 times n. So we're going to take 1,000 the first time out of range, the second time 2,000, all the way up to 100,000. And we're going to flip 2, and all this does is flip. It just does an increase and an ink and a deck. And if you say flip 3, it says ink, deck, ink. If you say flip 4, it says ink, deck, and you end up with the same number again, if it's an even number of flips. Just to exercise this sequence coming through. And if you have 2 of those mappings over this increasingly expanding sequence, this is the output that you get. And you can ignore the blue because that's the pipeline one that I was playing with before, where you can see it has this edge case that you don't even want to touch. You don't want to deal with. You don't want to accidentally shoot yourself in the foot with that version. But when you're dealing with this transformation right here, when you do the purely transducifying version, which has no parallelization, that's the yellow one. And as you can see, it's beating both the red parallel version and the green just vanilla version with no optimization. You can see that the parallel version is beating the vanilla version slightly, which just goes to show you how forgiving Fold is. Fold is very forgiving, and as you can see, pipeline is getting beat by the traditional green version here. But let's change.
Sorry, can you just the line that goes exponentially near the top is the vanilla, no transducer at all. The version, is that correct?
No, the blue one that's going straight up, that's the pipeline, and that's kind of this is a broken.
Yeah, sorry, just to clarify, the pipeline is just creating sequence after each.
Pipeline is. No, pipeline's like Fold. It parallelizes, and it uses core async pipeline under the hood for parallelization.
Oh, and that is like the most expensive, really? Wow.
Well, it's because it's
I
broken.
think that it is his own version. I think that this is his own version of a different code, which is not in this presentation.
Okay, sorry.
Yeah, yeah, and what I'm doing, I didn't talk about it in this workshop because its performance is so bad in certain cases. So
I'd be interested to see the code of it at some point, if you can publish it just for.
it's still in the library. It's still in there. So if you go into the source code, you can see everything for pipeline
Oh.
there. It's still there.
Okay.
I'm just not advertising it because it has weird behavior. Could be fixed. That's why I'm leaving it there. If you want to go fix it or figure out how to get rid of these edge cases, then we would love that. But this is such a lightweight work profile. I call it a thin work profile, where you have a big sequence or increasingly large sequence, but very thin amount of work going over that sequence. Now let's look at 3 mappings, but where flip increases with n, just like the sequence length does. So eventually, to the end of our exercise, we're going to have 1,000 flips on each of these 3 mappings. And in that case, we can see that, okay, the pipeline version starts to act more normal, but it's still losing compared to the transducifying one and the vanilla version. But here is where the fold version is just stomping everyone else. You can see it's doing a great job. And so here is my point is, this is like kind of like your sweet spot. If you imagine the amount of work you do in your thread last situations, you might do this much work sometimes. Other times you might do this much. And that's your Goldilocks zone of where you can think of, when do I need to start thinking about the parallel version? But what's interesting is as your work gets significant, the difference between the transducing version and the vanilla version start to wash out completely. And it turns out, what I've discovered here in these tests is that if you're dealing with work that is heavy enough, Clojure's lazy sequences aren't that bad. The amount of time you spend boxing and unboxing between transformation steps is so small compared to the amount of work that you end up doing in your transformation step that it doesn't really matter. It's a wash between the two. And the only time you're going to get any benefit is if you try to parallelize, because you've reached that amount of work. So it's true that once your work gets heavy enough that the transducing version isn't that much better than the vanilla version, that's when it's best to start looking at the parallel version. So it's kind of like one hands off to the other. Here's another example that shows you when the pipeline version breaks even with the other 2 versions. And right around, what, 60,000 sequence length, we can see that it's starting to catch up, and it surpasses the other 2 once the work gets heavy enough. But still, it's getting spanked. But if we were to increase have a whole bunch of mappings, then we can see that with the most amount of work, the heaviest shapes of the work, there's really no difference at all between the vanilla version and the transducing version. And there's really no difference at all between the pipeline version and the fold version. So in almost all versions, fold beats pipeline, and so I'm just recommending that from now on, right now.
I think that pipeline is some kind of an edge case.
Yeah, it has an edge case.
No, it is something that handles an edge case.
Could be. It could be. There's situations where pipeline is more performant, and if you're dealing with the series of channels that really do have separate streams that aren't correlated, then it could be that pipeline wins over fold. But we're always going to have correlated inputs and correlated outputs when we're talking about a thread last situation. That's the point of it. We want to do transformations over a particular sequence, start with one, result in another. So that's just the nature of what we're dealing with here. further on, I went to go test this out on various cloud providers and their high core count servers. Tried 32 on Google, did 72 cores over on Amazon. And in general, what I saw was that as you add more cores, you get less efficiency, obviously, because of coordination overhead between cores. So the more cores, the more communication. And so you're going to lose some speed, even though you're adding more than you're losing for each core. But what I've found is after 32 cores, I'm not losing, I go up to 72 after that, I'm not losing more than 40%. And it's an open question as to whether the other ones, the 128 core, 256 core, some of these super high core count ones that are out there now, if they hold that 40% efficiency rate. And if they do, that'd be really fantastic. They might, though, keep on sinking, and that would be unfortunate. But I'm glad to hear all the news recently out of AMD and Intel about their super high core count CPUs that they're targeting for the desktop space here in the next few years. So all of the fancy multi-core capabilities that we've valued in Clojure for so many years, some of those values may come to fruition more so in the near term, now that higher core counts are hopefully coming down the pike here. When we first started banging on Clojure so many years ago, Rich Hickey, some of the original sell of the language was its concurrency capabilities and its parallelism safety and abilities. And it's unfortunate that a lot of those benefits didn't play out over time just because of the hardware ecosystem didn't end up going as fast towards parallelization as we were expecting. But we're starting to now. So a lot of these tools are going to get more and more useful as core counts go up.
Hey, John, have you done this on the ARM-based machines?
I've not. I got a request out to Oracle to give me access to their 256 core count ARM server. Haven't had a chance. They got back to me and I've been trying to get set up on there. I haven't got a chance to do it yet, but that is going to be a pretty awesome test. And I've heard from others that they're excited about that as well. Let's see if there's anything else on the agenda I wanted to touch before the end here. I did have two ideas for just workshop stuff to do. One was to run through a Kaggle example of data cleaning. I don't think we have time. Yeah, we're getting towards the end here. So perhaps we can do it another time.
Is there a link to your workshop examples by any chance that we can use?
So this project that I threw together just to, in a REPL, go over stuff with you, I have not put up yet, but I can put this, I'll probably put it on a gist. I'll clean it up and make the examples a little clearer, but it'll follow the same flow that we used in this workshop. And so you can use that as source material too, in conjunction with this workshop. And I'll put it on a gist. On GitHub gists.
Thank you. Great presentation.
Thanks. Yeah, let me just open the floor up to the crowd here and get all the questions anyone can think of over the next 10 or 15 minutes, however long Daniel and folks can hang out.
Well, I have a comment regarding transducers that they make Clojure even more of rocket fuel than before they came on the scene. And I remember reading a blog or maybe a presentation, I forgot, but definitely Rich Hickey said that once he discovered them, well, or started to integrate the transducers into Clojure.core, he said that if he had the port, if it was possible, he would have made the Clojure core transducer the primitive rather than sec, the API primitive, because it's so fundamental. And
I remember when he said that, yeah. And it certainly piqued my interest, and a lot of other folks too were like thinking, well, what if we went and made a version of Clojure that was built on transducers from the ground up? And I think a lot of the people have been thinking about that ever since Rich mentioned it. But I will tell you, after playing around with these macros, which make it so easy to simply act as if we had that Clojure language that was built on transducers from the ground up. Because this is pretty much close to the semantics that you get anyway in that language. I started asking myself, well, what would be the benefit of that now? Your default function constructions would blow up on infinite sequences. So you'd have to use some kind of streaming library and bolt it onto the language just so that you could do the streaming things. Whereas right now, the streaming laziness is the default. And I think that what we're ending up with now is a language where the default is more of a scriptable kind of thing, more of a scripting language where you can effortlessly talk about infinite things or endless things without worrying about stuff blowing up or having to bring in a streaming library to talk about those things. And now when we want the more eager jet fuel version, it's pretty much simply a different thread last macro away. And so I don't really know what the benefit of going all transducers all the time would be in lieu of this, but it would be interesting to see. I'm sure it would benefit some scenarios, but I think I'd rather have, personally, the more scriptable, forgiving version we have now. So, it's not that.
If Richard think he would be able to redesign the language, I think that he would be tempted to use iterators more.
Yeah, that's what I'm hearing, is that, yeah, the going with iterators, and I guess some stuff does under the hood. I guess over the last few years, a lot of stuff under the hood has been moved to that. I think Range produces an iterator as well, and yeah, there's a bunch of areas where optimizations are happening, and there's areas for improvement, but pretty much the usability has not been affected. Things are still very forgiving and usable.
What I meant by mentioning iterating, so it would be a different language.
Yeah, so any more questions?
Maybe let us try to come close to conclusion. And yeah, so a few short questions would be wonderful. And otherwise, maybe, John, you would like to conclude and say a few words to the end?
Sure.
And that was a wonderful discussion. One of those cases where we feel there is more to discuss. So if you would like to have another workshop, then John, it would be wonderful if you could. And thank you so much, Martinas and JF and Florian and Jose, for all your comments. It was a wonderful discussion.
Appreciate it. Yeah, and I very much like to. things that I did want to be able to cover that we didn't get around to. So maybe if I have time to put together maybe a run through of the Kaggle example of what you do with data cleaning. If there's a situation where you don't want to yet use dtype next, or you have a number of transformations that don't yet avail themselves to dtype next tools that you can accomplish in just the generic Clojure world, just to get the data ready to put it into dtype next, for instance, then maybe this might be useful for that. I should actually, there's my cowboy hat. We didn't get into the wrangling, so I don't think it was really worthwhile wearing the cowboy hat, but maybe next time we'll wrangle some more data together. Little story behind the cowboy hat. Rich Hickey, in his presentation about transducers, he said that this was kind of like an ingestion process. And so that's where I got the name Injest from. But since it has the word jest in the name, I had to make something funny for this presentation. And I figured, well, what does wrangling do? Well, it's like a cowboy that cowboys do wrangling. And well, we didn't get to wrangle much data today. We just went over the details. So maybe in a follow-up presentation, we'll get into the actual wrangling a little bit more.